Hello everyone. Today we are going to start in the first topic in our Analog Electronics class. So we will start discussing today the semiconductors. Before we starting, just I would like to remind you guys, please have a look to eCampus regularly to check if there is any announcements. Uh, Today early morning, I made an announcement regarding the lab. So the lab is going to start in week number 3. Because for any lab, guys, we need to have some background for the class materials. So we have to finish some materials in order to start make some application for sure. So week number 1 or week number 2 may not be, we may not have enough time to make applications for the analog electronics class. So therefore, let's say we're gonna start in week number 3, and hopefully by week 3 we will reach to enough materials to make the first experiments. So today we are going to discuss about the semiconductor materials. So what are the semiconductor materials? We will discuss in detail. So the topics today, or the objectives of these materials, we may finish this material today. If we couldn't finish today, we will continue this material in the next class. So the objectives of the first material is objectives are gain a basic understanding of few semiconductor material properties. So what are the properties of the semiconductor material we need to understand? We will discuss it. Recognizing the two types of charged carriers that exist in a semiconductor material. So what the meaning of carrier? So we will discuss the meaning of carrier and what are the two different types. And finally, learning the two mechanisms that generate current in a semiconductor material. Most probably the last objective will be covered in the next class. So let's start together from scratch to remember the meaning of semiconductor material. I'm certainly sure that all of you guys learn in physics or in chemistry the atoms and the distribution of electrons, but how this will affect the current flow and what are the different types of conducting material. So this is what we are going to discuss today. So start, guys, from the very basic thing about the material, which is atom. So this is a shape of an atom. So we have something inside, we have something outside with different colors and polarities. So let's investigate or remember together what are the different charges and objects we have in an atom. So firstly, the atom consists of a nucleus. So the nucleus is the internal part, and electrons. Electrons are the charges, the negative charges in the output shells of the atom. So the internal objects inside the nucleus are called uh, protons and neutrons. So since we have neutrons and protons inside the atom and we have negative charge outside the atom, we can say the atom is neutral. Neutral means it's balanced since the total number of charges are the same. So the nucleus is positively charged. So inside the nucleus itself, it's positively charged. Why it's positively charged? Because it has the following. It contains the protons, and protons are positively charged particles, and also it includes the neutrons, and neutrons are electrically neutral particles, which means it has a neutral, electrically neutral, which means it has no polarity. Okay, let me find the pointer here. Yeah, so inside here these bodies, we have inside the nucleus, we have positive charges. The positive charge is called proton, and we have neutral charge. So this one object here, it's called a neutron, and as you can see, we have no signs, which means it's not positive or negative. So this is neutral. So since we have positive and uh, neutral charges inside the nucleus, so the total charge of the nucleus itself is going to be positive, and the atomic number, as you can see, we have here a number called 6. Okay, so 6 here is 6 protons, and we have also 6 neutrons inside. So we have a number called atomic number. What's the atomic number? The atomic number is the number of protons in the nucleus of an atom. So for this element, for instance, this is, by the way, this is carbon. So since we have 6 protons inside the nucleus, so this means the atomic number of this atom of the carbon is 6. We have another number. So we just guys reviewing together the information or the basics of atoms and materials. So the mass number is the sum of the numbers of protons and neutrons in the nucleus of an atom. So summing the numbers of protons and neutrons inside a nucleus, so this is called the mass number. So the mass number is for sure higher than the atomic number for any material. What about electrons? So we said that we have electrons in the output shells, and these electrons are negative charges. So the electrons are negative charged particles that revolve around the nucleus. So it's like our universe, guys. So for the universe, we have the sun, we have and other objects rotate around the sun, Earth, and other planets rotating around the sun. So the atom is the same. Anything in the universe have the same shape. So inside we have the nucleus, outside we have the electrons, and these electrons are revolving around these or the nucleus inside. The number of negative electrons in the output or the outer shells, the number of electrons equals the number of positive protons in the nucleus, which means in this atom, for instance, when in carbon atom, we have 6 protons, so we have also 6 electrons. So as you can see, in the first shell here, we have 2 electrons, and in the outer shell, we have 4 more electrons. So the number of total electrons here are 6 electrons. So electrons equals the same number of protons inside the nucleus. So the number of negative electrons equals the number of positive protons in the nucleus, so that the atom is electrically neutral in its ordinary state. It's very important, this word, guys. It's in its ordinary state. Ordinary state means at normal operating conditions without any external applied energy. Okay? So let's agree together that the ordinary state means we don't have any external energy applied to the material or to the atoms. Okay, let's see an example, guys, for one other element here, like aluminum. So for the aluminum, we have here 2 numbers. The upper number is the atomic number. So this is the atomic number, it's 13. And the lower number here, 27, is referring to the mass number. So we can say from this uh, symbol, from this element, aluminum, we can say that the aluminum has 13 protons or 13 electrons, and the number of neutrons inside the nucleus equals the difference between the mass number and the atomic number. So 27 minus 13 is 14. So this atom has 14 inside neutrons and 13 protons and electrons. So this information can be obtained just if we have an element with the well-known numbers of atomic number or mass number. Therefore, the atomic number is 13 and the mass number is 27. Let's solve these together, guys, as a training now. So here we have silicon. So silicon is one of the materials. We will discuss it too much in our class because this is one of the semiconductor materials we are going to use in most of power electronics or electronics components. So guys, for this element now, how many electrons we have? So the first question here, the atomic number of the silicon is, hmm, so according to our discussion in the previous slide, so the atomic number should be now 14. So this is the atomic number. So this is the answer here, 14. The mass number of silicon. So the mass number is the number here in the bottom. So this is here 28. The number of electrons in silicon atoms. So we mentioned together, guys, electrons and protons are equal numbers and both are equal to the atomic number. So this should be also here 14. The number of neutrons in silicon atom. So we said that the neutrons are the neutral charges inside the nucleus. And in order to get the number of neutrons, we need to subtract the mass number minus the atomic number. So 28 minus 14. So it's also 14 for this element. And finally, the number of protons in silicon atom. So we mentioned together protons and electrons are equal numbers and both are the same as the atomic number. So we are right. The number is 14. So this is the answer of this question. Okay, now let's go more in deep and see, guys, the electrons configuration. So how can we have electrons for any element? In order to understand that, guys, there are some theory. For sure, you know this theories. You already learned that maybe in chemistry. So there is one theory for a guy called Bohr. So Bohr, he made a theory regarding the what's called orbit. So the scientist Bohr was the first scientist to give an idea of the atom's orbit. So the orbit, guys, is gonna be the shell that will contain or carry the electrons, or let's say the electrons are gonna revolve inside this shell or this orbit. So this is the definition of Bohr. The electrons of the atom revolve around the nucleus in a certain circular path. And this circular path is referred to as orbit or shell. Okay? So this is now the place that the electrons are going to rotate around the nucleus. It's called orbit or shell. Orbits are expressed by n, where n can be 1, 2, 3, 4, and so on. So this is a serial number of the orbit. So we have orbit number 1, 2, 3, 4, and so on. So for any atom, we will have some number of orbits or shells around this atom or around this nucleus. And also, Bohr gave it some letter names. It's not only numbers. So he gave a name of letter K for the first orbit, letter L for the second orbit, and M and N for the third and the fourth orbit. So now we have a question. How many electrons can be carried or revolve in every shell or in every orbit? So there is a relation for the capacity of every orbit. The relation is 2 times n to power 2. So n is referring to the orbit number. So the orbit is 1, 2, 3, 4, and so on. And in order to give the capacity, how many electrons the orbit can carry, so we can use this relation now. So if you substitute in this relation, guys, at every shell, so for shells KLMN, K is number 1. So substitute here in the relation, you will find that the first shell can carry 2 electrons. The second shell, called L, can carry 8 electrons. How? Simply 2 is the number of shell. 2 to power 2 is 4 times 2, so we have 8 electrons can be carried in the second shell. By the same way, so M orbit has number 3, so 3 to power 2 is 9. 9 times 2 is 18, so orbit M can carry 18 electrons, and finally orbit N, or number 4, can carry up to 32. If you have other elements with more or higher values of electrons or atomic numbers, so you can make 5, 6, 7, and so on. Okay, so this is the theory of Bohr, how the electrons can be distributed around the nucleus in the atom. Let's see, guys, one of the elements, we are going to use it also a lot in electronics and power electronics. It's called germanium. So this germanium, the atomic number is 32, which means we have 32 electrons in the atom or around the nucleus. How can we distribute these 32 electrons? So according to the discussion in the previous slide, we said that, let's go back one more time. So we have the first shell will carry 2 electrons, second shell will carry 8 electrons, third shell will carry 18 electrons, last shell can carry up to 32 electrons, and for sure according to the number of electrons we have. So for the germanium is 32, so we have 2, 8, then 18, so 2 plus 8 is 10, plus 18, it's 28. So we will have remainder 4 electrons. So this means in shell number 1, we will have 2 electrons, as you can see. In shell number 2, we will have 8 electrons. It will be distributed around the nucleus. And by the way, this is 2D plan. If it is 3D plan, you will see a different shape. But just for simplification, let's make it 2D for the time being. And then 18 electrons can be distributed in the third shell, and the remainder of 32 is going to be just 4 electrons. So the remainder 4 electrons will be exist or revolve in the fourth shell. So this is, guys, the distribution of the electrons or the configuration of the electrons of the germanium elements. Let's see the silicon. Silicon is also going to be used a lot, as we mentioned. So for the silicon, the atomic number is 14. So this means we have 14 electrons. So this can be distributed as 2 in the first shell and 8 in the second shell. So 2 plus 8 is 10. So we will have just remainder 4 electrons. So the last 4 electrons can be distributed in the output or the outer shell of the atom, as you can see. So this is the distribution of the electrons in any atom. Now, In order to go more in deep and understand more about the semiconductor, guys, we need to remember together the idea of material, the conducting material, the insulating material, and the then we will investigate more what the meaning of the semiconductor material. But let's see a video together to remember how the electricity is moving inside materials. So let's see this video together.
Electricity is vital to our civilization. So what is electricity and how does it work? To explain electricity, we need to zoom past the molecular and into the atomic level. Atoms are the smallest things we can kind of see, but not with the naked eye. Only with a scanning, tunneling microscope can we get a glimpse of somewhat fuzzy spheres. To really understand electricity, we must go even further and look inside an atom. This is where it gets complicated, because the inside of an atom cannot be seen, at least not at the time of writing. So we will use this representation of the inside of an atom. This is called the Bohr model. Keep in mind that it is not to scale and only two-dimensional. This model is also known as the planetary model, modeling the parts of an atom as planets orbiting a sun or moons around a planet. While actually these orbiting moons are not at any one place at any one time at all, but exist more as regions or clouds around the core. However inaccurate the Bohr model might be, it will do for our explanation of electricity. Atoms consist of protons and neutrons. These form the nucleus of the atom. Orbiting the nucleus are the electrons. It's these electrons that are responsible for electricity, hence the name. Think of these orbits more as shells surrounding the nucleus. What type of atom, which element it is defined by the number of protons in the nucleus at the center. Atoms of one element all have the same number of protons, but can have different numbers of neutrons and electrons. It's this variable number of electrons that is important to our understanding. Electrons, which are far lighter than the protons in the nucleus, can relatively easily move. And this is important because the movement of electrons is what forms an electric current. The atom's protons account for the positive charge of the nucleus, and the electrons for the negative charge. In a stable, resting, or rather neutral electrical condition, these charges balance each other out within the atom. This gives the atom a net electric charge of 0. For each positive proton, you will find one negative electron. In this state, the atom is at its lowest possible energy level, which we call the ground state of the atom. However, we can change the atom's charge or energy level by causing it to gain or lose electrons. When the atom has fewer electrons than protons, it becomes positively charged. But when the atom has more electrons than protons, the net charge swings back the other way and it becomes negatively charged. More electrons than protons mean the atom is negatively charged. Fewer electrons than protons mean it is positively charged. Losing or gaining electrons changes the atom's electric charge. The remainder of this video we will color code the atoms as follows. A positive charge or absence of electrons is represented with red. A negative charge, a surplus of electrons, is represented with blue. A neutral charge or a balance between electrons and protons is represented by a blend of red and blue, purple. So when in a ground state or uncharged, it looks like this, and it's called an atom. When charged, negatively or positively, it looks like these. Instead of atoms, when there is a charge, these are called a negative or positive ion. Each shell of an atom can hold a maximum number of electrons. The inner shell can hold 2 electrons, the second can hold 8, the third 18, and there are elements with all 7 known shells. Shells are populated with electrons from the inside out, meaning that added electrons always go for the innermost shell possible with a spot left. The number of electrons on the outermost shell determines the reactivity of the atom. This shell is called the valence shell, and its electrons are called valence electrons. When the outermost shell is full, the atom is generally stable and least reactive. You may be familiar with the term and effects of static electricity. When you, for instance, shuffle your feet over a nice soft carpet, you build up a positive charge, because negatively charged electrons are being lost to the carpet. Carpets are often made from a material with the properties of an insulator. Insulators do not easily give up electrons but can get a local charge when electrons from a conductor are rubbed off on them. An insulator's valence shell is already quite full of electrons. These electrons will just sit there until something else takes them away. However, your body is a conductor. Conductors have loosely bound valence electrons which are easily transferred or lost, in this case from your body to the area of the carpet where you're shuffling. Instead of you and the carpet having a neutral charge, a charge imbalance is being created between you and the carpet. Now, when you touch a metal object, for instance a doorknob, you get zapped. The doorknob may be neutrally charged, it is metal, and metals too are conductors with loosely bound electrons on the outer shells of their atoms. These electrons immediately move to your body to restore the charge imbalance, giving you a jolt. Nature always seeks a neutral charge equilibrium, a net charge of 0. Materials with high electron mobility are called conductors. Materials with low electron mobility are called insulators. A commonplace object where you can see an insulator and conductor working together is in a simple wire. This electrical wire has a copper core and a plastic shell. Copper atoms have a very loosely bound electron on the outside, as seen here again using the Bohr model. This makes copper a perfect conductor, whereas the plastic is an insulator. The millions, if not billions, of copper atoms in this piece of wire easily exchange electrons, allowing us to make an electrical circuit with it. Think of an electrical circuit as a path that connects 2 points with a possible charge imbalance, usually connecting a negatively charged point to a positively charged point. Like marbles in a tube, moving from a high place full of marbles to a low place lacking marbles. Imagine these marbles all along the circuit, each marble being an electron. These marbles originate from a power source, for instance a battery. And we'll explain how batteries work exactly in a future video. Electrons move from the negative to the positive, as we've established earlier. The battery pushes out electrons from one end and attracts them from the other. As one is pulled in, one is pushed out. Despite the electrons moving relatively slowly, this effect causes the energy to be transferred almost instantaneously. To create such a flow of electrons, we must provide them a path with a conductor, such as the copper within our wire. If this path is blocked by an insulator, such as plastic, rubber, or air in the case of a cut wire, the electrons cannot continue to flow, stopping the electric current. The key to the flow of electricity is making a continuous electrical circuit, connecting a wire between a source of electrons and an attractor of electrons. All electrical devices are powered this way. That is why your battery has 2 poles, a source and an attractor, a negative and a positive. This is also why your electrical plug has at least 2 tongues, one for incoming electrons, one for outgoing. You see, electrons are not spent, they do not cease existing. They are mere carriers of charge and can only be useful on their way to their destination. Take note, that connecting two poles of a power source directly can actually be very dangerous. This is what's called a short circuit, because there is nothing between the source and the destination of electrons to power, such as a lamp or television. This means that the electron flow will not encounter any resistance. The release of energy when short-circuiting is therefore instant, often paired with the involved wire heating dangerously. This is why buildings and some devices have fuses. These automatically cut the current flow when the current becomes too high, preventing damage or worse. In the next videos on electricity, we'll learn more about generating power, resistance, voltage, amperes, batteries, fuses, motors, transformers, and more. Subscribe and hit that bell.
Okay, guys. So as you could see, this is an interesting video uh, discussing the meaning of electricity, how the current is moving based on the electrons, and now we can have some questions. So we can classify the materials now to insulators, which means it has very high resistance and doesn't have any kind of free electrons to move, and not possible to move electrons easily because it may need very high power to initiate current flow or to initiate electrons flow. So this means if you have a supply connected to an insulator, there will be very few electrical current can flow, but this current we call it like leakage current. So leakage current, why? Because still the insulator material has very huge resistance. So theoretically, it's not infinite resistance. It will have a value of resistance. So if you apply Ohm's law, if you have a battery and you have a certain resistance, so I equals V divided R, which means even for the insulator, you may have a current in very few, uh, let's say, nano amperes, okay? And nano ampere cannot be detected, which means for us as zero current. So we can consider this as insulator. And we have a conducting material, which means it has free electrons, and these free electrons are ready to move even without applying a supply. As you could see, just when the guy had a few uh, missed electrons and he taught with his finger, he taught the material. So what happened is some free electrons start moving from the metal to his hand, but this is static electricity. So this is conducting material. So the conductor material doesn't need like amount of energy in order to flow the current. So once you have any kind of supply, even a very small value of supply, this can initiate current. And this is at any temperature. Any temperature means we don't need to apply any kind of energy in order to initiate electrical currents. But we have now something else called semiconductor. So what is the semiconductor, guys? So the semiconductor, now we will have some electrons, but these electrons need some energy in order to allow the electron motion and allow a current flow. So we can conclude that semiconductor is a material that in between insulator and conducting material. But it doesn't mean it has like average resistance between both. No, it has just controlled resistance, which means we can make the semiconductor material as insulator and we can make it as very good conducting material with very small value of resistance. But the difference between conducting and non-conducting material, sorry, the difference between semiconductor and conducting or insulator is we can control the current flow of the semiconductor material. But for conducting material, you cannot control because it has definite resistance. Once you have supply, an electrical current has to move. But this is not the case in semiconductor material. Let's go more in
Electricity
deep and see Sorry. Let's see, guys, now the or more discussions about the semiconductor material. Let's start with the silicon. So this is the shape of the silicon crystal. Crystal means some electrons, sorry, some atoms are connected together. So we have here, for instance, one, two, three, four, five atoms of silicon, and we agreed together that for silicon 14 we have four electrons on the outer shell. So every dash here around the silicon atom can represent one electron. So what happens here is every two atoms together will be connecting the electrons together. So as you can see now, this silicon, let me get the pointer here. So this silicon atom has one electron along with this silicon atom, so they made two electrons together. So there is a bond now between the two silicon atoms. But since the silicon has four electrons in the outer shell, so it can connect to it can be connected to four atoms around it. So as you can see here, this is called silicon crystal, and the bond between every two silicon atoms is called covalent bond. Okay, what does it mean? What does it mean we have a bond? Actually, bond means it's like uh, something make coupling between the two atoms, which means if you would like to release the electron now, you have to have some energy. You have to consume some energy in order to allow the electron to be released. And releasing electron means current flow. So this is the concept, guys, now. If you would like to allow the semiconductor material to flow a current, you have to consume some energy. Once you consume this energy at a certain amount of energy, you will flow the current as if the material is a conducting material with very small value of resistance. And this resistance, later on, we will discuss how can we control the resistance of a semiconductor material. Okay, now let's see, guys, if we have a two-dimensional scene for a crystal silicon here. And as you can see, every silicon atom is connected to another silicon atom by means of two electrons and making a bond in between. So here in this figure, guys, a two-dimensional representation of a silicon single crystal is shown. And this is at T equals 0 Kelvin. 0 Kelvin means you don't have any energy in the silicon now. So no energy is applied to this silicon crystal. Each line between atoms represents a valence electron. So we said the line here represents one electron, and this is called valence electron. If a very small electric field is applied to this material, the electrons will not move. So very few is not sufficient. Very small electric field is not sufficient. It needs a certain amount of electric field in order to allow the electron to be released, in order to break the bond between the different atoms. So the electrons will not move because they will still be bound to their individual atoms, because it has a certain energy. And in order to release this electron, you have to break this bond. Therefore, at T equals 0 Kelvin, silicon is an insulator material, so it cannot conduct any current. That's no charge flows through the atoms or this through the crystal of silicon. So this is at 0 Kelvin, since we do not apply a source of energy to the crystal of the silicon. Now, if the temperature increases, the valence electrons may gain thermal energy. And temperature increase means you applied a certain amount of energy. You applied an energy in order to increase the temperature of these elements, in order to break the bond between the atoms. Any such electron may gain enough thermal energy to break the covalent bond and move away from its original position, as schematically shown in this figure. So once you apply energy with a certain amount, the electron can break the bond with this amount of energy and uh, start moving between the atoms. And once electrons start moving, so this means electrical current can flow. So this is the concept. We need a certain amount of power. We need a certain amount of energy in order to release the electron and move the electricity inside this uh, semiconductor material. Now, the title of this slide, how to break the covalent bond now. How can we break, guys, the covalent bond? So this is called crystal energy band. What the crystal energy band? In order to break the covalent bond, the valence electron must gain a minimum energy. This energy, we call it Eg, or band gap energy. Band gap energy. So if you apply or deliver this band gap energy to an electron, the covalent bond can be uh, uh, broke, and the electron will be free to move and allow a current flow. In order to understand these, guys, assume that here we have these two figures here. We have different levels of energy. So we have what's called valence band. We have what's called the conduction band. And the electron can move if you applied a certain amount of energy called the band gap energy, in order to allow the electron to move from the valence band to the conduction band. Okay, the electrons that gain this minimum energy, the band gap energy, now exist in the conduction band. So conduction band means you conducted current, so the current can start flow because you have free electrons now. Okay, so now the electron can be exist in the conduction band and are said to be free electrons. Free electrons means you have a current flow. So this is the concept now, guys. In order to allow free electrons to move, you have to apply or energize these electrons by certain energy in order to make breaking for the covalent bond. These free electrons in the conduction band can move through the crystal, which is referred to as electrical or current flow. So this is, guys, the meaning of current flow, and you could see the current flow already in conducting materials in the previous video, but now we are discussing about the semiconductor material. So once you apply a certain amount of energy in order to break the covalent bond, so you will have free electrons, and once you have free electrons, this means a current will flow in the semiconductor material. How much energy we need? So we need to relate this energy to the supply volt. For that, there is a definition called electron volt. So the electron volt is nothing but the energy of an electron that has been accelerated through a potential difference of 1 volt. So the energy that the electron will need corresponding to 1 volt is called the electron volt. And 1 electron volt, guys, equals 1.62 times 10 to power minus 19 joules. So this is the energy corresponding to 1 volt. Now, materials have different characteristics. So we have conducting material, we have insulators, we have semiconductor materials. How much energy we need for every material to allow a current to break the bond and start moving. So for the materials that have large band gap energies in the range of 3 to 6 electron volts, we call it insulators. So let's say 6 electron volt is insulator. So in order to allow a current flow in insulator, you need to apply energy more than 6 electron volt for instance. And it's not going to be constant for every material. It depends on the material type. But let's say common, from 3 to 6, it can be considered as insulator. Okay, guys? On the other hand, the conductors, in contrast, material that contains very large numbers of free electrons, like copper, okay, at room temperature, which is 300 Kelvin, are conductors. So we don't need to have energy in order to flow the electrons. Once you supply the or connect electrical supply to the conducting material and alloys, you have a closed loop, so a current will start flowing because you have a lot of free electrons of this material. And for a semiconductor material, the band gap energy is in the order of 1 electric volt, around 1 electric volt. So it could be less than 1, around 1, 1.1, something like that. So the range around 1 is called the semiconductor, or the energy needed for a semiconductor is around 1 electric volt. Okay, guys, 1 electron volt. So this is like a summary now for the different materials. So insulator can flow current if the energy is more than 6 electron volt. And 6 electron volt, by the way, guys, is very huge amount of energy. If you apply, for instance, on wood, so the wood may be burned because flowing electric current in wood means electrons is gonna move. This means the wood is gonna be burned. Okay, guys. So for sure, this is gonna damage the insulators in order to flow current. So this is a summary for the energy levels we need in order to flow current in the different materials. Let's solve these questions together, guys. So here in this question, to initiate an electrical current in a semiconductor material, 0 electric volt is required, 3 to 6 electric volt are required, around 1 electric volt is required. No right answer. Yes, I can hear you. Around 1 electric volt is required. This is in a semiconductor material. But if I said, guys, instead of semiconductor material, to initiate electrical current in a conducting material, so this means 0 electric volt is required. You don't need any electric volt to initiate the motion of current in conducting material because the conducting materials already have a lot of free electrons. So you don't need to release these electrons in order to allow a current to flow. Okay, guys? So this is again the definition. The definition of electric volt or electron volt is the energy need to break the bond to allow free electrons to move. So in conducting material, we don't need to do that because we have already free electrons to move. But in semiconductor material, we don't have free electrons to move. In insulator material, we don't have electrons to move, and the bond energy is very high, which means it needs very high energy to allow a current to flow. Okay, guys? So this is the answer of the first question. The second question, which of the following is most probably uh, energy needed to initiate electrons moving in an insulator material? So we just mentioned, guys, for insulator materials, we need huge amount of energy. It can be from 3 to 6 electron volts. So here in the Multiple choices. We have applying energy greater than 6, applying energy of 1, no right answer. Actually, applying energy greater than 6 electron volt will allow the insulator material to initiate the electrons to move in the material. So the correct answer here is A, applying energy greater than 6 electron volt. Now, since we understood the concept of what the meaning of free electrons, what the meaning of covalent bonds, how can we initiate an electron to move inside a semiconductor material, let's see together now, guys, what the level of electricity we can have from a semiconductor material. In order to do that, guys, we have what's called intrinsic semiconductor material. I'm not sure if you can see the title, but I can move this here. So we have intrinsic semiconductor material. What's the meaning of intrinsic semiconductor? And since we have intrinsic, so we should have extrinsic. So let's see together, guys, step by step, what the meaning of intrinsic semiconductor material. The excited moving electrons, which is the negative charge, will move to a positive charge, which is called a hole. So once you initiate or gave some energy to the electrons inside the silicon crystal, so this means some electrons will start to move, but move to where? So electron is a negative charge. In order to move, it needs to be connected to a positive charge. And the positive charge is nothing but the free space in the atom after another electron is moving, which is called hole. So we have now hole, which is positive charge, and electron, which is negative charge. So any electron will move to be connected to a hole in order to move. Otherwise, where the electrons will move. So in the semiconductor now we have two types, guys. Two types of charges. We have positive charges, which is called hole, and negative charges, which is called electrons. So the negative charged free electrons and the positively charged holes. These are the two different charges we have inside the material once you applied energy and there is some electrons start moving inside this material. So we have n n electrons and p holes, negative electrons and positive holes. The concentration of electrons or holes, which is measured by number of charges per cubic centimeter, these concentration are directly influence the magnitude of currents. So if you have the high concentration of electrons or holes in a semiconductor material, this means this will allow a higher current to flow. So let's see what the meaning of concentration or how can we make the calculate the concentration for the materials. And until now we didn't discuss what the meaning of intrinsic. So now this is the time to discuss the intrinsic. An intrinsic semiconductor is a single crystal. Single crystal means it has one type of atoms. One type means one element. So all the crystal has silicon atoms. So since it's one material, we call it intrinsic semiconductor. Okay, guys. So an intrinsic semiconductor is a single crystal semiconductor material with no other types of atoms within the crystal. Let's see, guys, the concentration. How can we calculate the concentration of an intrinsic semiconductor material? For the intrinsic semiconductor material, the concentration is called Ni. So Ni is referring to the number of uh, electron, or let's say the number of charges per cubic centimeter. So the unit is number per cubic centimeter. And in order to calculate this number, this is the relation. B is the scaling constant, its coefficient, and this coefficient is vary according to the material. So every material has its own coefficient. For instance, here in this table, for the silicon, the B value is going to be 5.23 times 10 to the power 15. For sure, in problems, you will have these constants given in the problem in order to solve any problem in the exams or anywhere. So this is the first constant here, B, multiplied times T to power 3 over 2, where T is the temperature in Kelvin, and the room temperature in Kelvin is 300 Kelvin, and exponential function minus Eg. Yes, we discussed this Eg before. We said Eg is the energy or the band gap energy and measured in electron volts, and divide 2 kT. K is constant, which is Boltzmann constant, and this constant is 86 times 10 to the power minus 6 electron volt per Kelvin. You don't need to memorize these constants. It will be given in any problem. And also multiply times T, again, the temperature in Kelvin. So this is the relation, guys. How can we calculate the concentration of any intrinsic material? So N intrinsic equals B T to power 3 over 2 exponential minus Eg divided 2 kT. By the way, guys, in exams, you are allowed to have a formula sheet, so you can summarize the formula sheet. And I do recommend you can type or write down in your formula sheet anywhere. You can write the constants that will be used. For instance, Boltzmann constant, it's constant whatever the material, so you can write this down in your formula sheet just to remember it. But other numbers like B or electron volt for any material, this will be given in any numerical problem. Okay, guys, but you are free to write down the relations in your formula sheet in any exam. Okay, let's apply one material here to see how can we calculate the concentration. So here in this example, we need to calculate the intrinsic carrier concentration in silicon. So we have silicon atom, and we need to calculate the intrinsic carrier concentration. Intrinsic carrier concentration, guys, this is for the free electrons. This is for the electron that will move between the silicon atoms. Okay, so we need to calculate this intrinsic concentration at a temperature of the 300 Kelvin, which is the room temperature. Again, I got the numbers from the previous slide. So for the silicon material, we have the electron volt energy needed, which is 1.1 electron volt, and the constant coefficient B is 5.23 times 10 to the power 15. Now, just substitute in our equation. So we need to get the intrinsic concentration of this atom. So we can say now B times T to the power 3 over 2 exponential minus Eg divided 2 kT. Just substitute, guys, with the numbers you have here. So you will get the concentration is 1.5 times 10 to the power 10 per cubic centimeter. So this is the number of intrinsic carriers we have per cubic centimeter. So for any die, for any semiconductor material, guys, in any switches, we call it die. In any die, guys, we care about how many carriers we have per cubic centimeter. If you have more carriers per cubic centimeter. So this means this material is uh, most probably will provide more current or can allow more current, and it will have very small resistance. Later on, guys, in our classes, we will discuss some materials. It's used now in industry, like wide band gap semiconductor materials, like silicon carbide, like gallium nitride, and we will discuss the difference between the intrinsic and and extrinsic soon, to see how the concentration is very important if we have extrinsic material. Okay, so for the time being, if this number is high, this means this material is providing or can allow more energy to flow, or can transmit more energy to flow, or can allow more current to flow in it. Just comment, an intrinsic electron concentration of 1.5 to 10 power 10 may appear to be large, but to be honest with you guys, it's not that large, because the concentration of the silicon atom itself is 5 times 10 to power 22. So this is the concentration of the atom itself, but this is the concentration of the intrinsic electron in the silicon atom. Okay, guys. So this number is not that large compared to the atom itself. Okay. Now we discussed the intrinsic. Let's see the extrinsic. What will happen if we add another material to the silicon? What will happen? Is it gonna make more concentration? Is allowing more current to flow or not? Let's see this if we add another element to the silicon. For instance, this is extrinsic semiconductors. So since electrons and hole concentrations in an intrinsic semiconductor are relatively small compared to the atom concentration, only very small current are possible. So we can flow current, but it's still very small, guys. We need to have more current to flow. So having intrinsic semiconductor material is not enough. We need to add something else in order to allow more current to flow. And we could see the number. So the number of concentration compared to the atoms, it's very small. Actually, if you compare 10 to power 10 to 10 to power 22, it's a very big difference, actually. So this is not a big number. So in order to improve this number, what should we do? Let's see if we make what's called injection for the material by another material. And this is called the extrinsic semiconductor. So if we add another material, and we can call it impurities, because the major number of atoms will be the main material, which is silicon, but we will add very few other atoms inside here. So we call it impurities. So the impurities will affect the concentration. Let's see this together. Let's add the phosphorus. The phosphorus is 15. So the silicon is 14, which means now you have one free electron. If you add the phosphorus to the silicon, you have one extra electron actually here. Okay, so this is gonna improve the current probability to move. So for example, when phosphorus atom substitutes for silicon atom, as shown in the figure here, 4 of its valence electrons are used to satisfy the covalent bond requirements. 4 electrons of the phosphorus are gonna connect to the silicon to satisfy the covalent bonds. But we will have one extra electron now. So at the room temperature, 300 Kelvin, this fifth electron has enough thermal energy to break the bond just at the room temperature, guys. So at 300 Kelvin, this free electron can break the equivalent, the bond, and start moving. So break the bond, thus being free to move through the crystal and contribute to the electron current in the semiconductor. So when we added now the phosphorus, we have one free electron at the room temperature, 300 Kelvin. It's enough to break the bond and start moving. So for sure, this will affect the concentration. So when phosphorus valence electron moves into the conduction band, a positively charged phosphorus ion is created as shown here. So in this case, the phosphorus itself became positive ion, which means it can accept an electron. So this is the idea, guys, now. One electron is moved to another hole, and another electron is going to be connected here. So this is the motion of electrons, and this is the electrical current motion or the electrical current flow in a material. In this case, guys, the phosphorus itself, we call it donor because it donates a free electron to the silicon crystal. The process of adding this impurity is called doping or injecting. So doping means inject another material to provide free electron. Okay. Actually, here it's free electron because it's donor material. But let's say the operation of adding impurity is called doping. Okay. Okay. And it allows us to control the concentration of the free electrons in a semiconductor material. A semiconductor that contains donor impurity atom is called N-type. Why N-type? Because we have one electron, or let's say here in case of the phosphorus with silicon, we have one electron, so this is negative charge, so we call it N-type. We may have more electrons. It's according to the material we are doping to our semiconductor material. The doping process determines the conductivity and the currents in the material. Why? Because as we mentioned, the more concentration, the more current can flow and conduct any current or connect any supply to load as if it's conducting material. Another example, guys, here we doped another material, not like the other one. Here we added boron. So boron is 5. If you distribute the 5, so first shell will have 2 electrons, second shell will have 3 electrons, which means now around the boron we have 4 silicon atoms, 3 of them are connected and 1 is empty. So we expect here this is going to be P material, not N material. And here, instead of doping, instead of uh, uh, donating, it needs an electron, correct? So needs an electron, we will call it acceptor. Okay, so this is the difference now, guys. If we have 3 electrons, the material is going to be donor. If we have less electrons, the material is going to be acceptor. So here in this example, guys, this leaves one bond position open at room temperature. Adjacent silicon valence electrons have sufficient thermal energy to move into this position and thereby creating a hole. So we have here a hole, not an electron. And for sure, this hole is ready to accept an electron. So this will allow to have more concentration in our material. This effect is shown in figure B here, guys, in this figure. The boron atom then has a net negative charge but cannot move, and a hole is created that can contribute to a hole current. Because boron atom has accepted a valence electron, the boron is therefore called acceptor impurity. So we have now donor and acceptor. Donor if we have electron or free electrons to move. Acceptor if we have holes to accept electrons. And we call these guys a p-type semiconductor. So the n-type semiconductor material, the carrier is negative charge, and the p-type semiconductor material, the carrier is positive charge. The n-type material, the carrier is uh, donor material, and the p-type material is acceptor impurity. How can we calculate the concentration? And we can end up with this relation today, and next class we will solve more questions on this part. So how can we calculate the concentration? Since guys we have two materials now, we can make a balance between these two materials by this relation. So a fundamental relation between the electrons and hole concentration in a semiconductor in thermal equilibrium is given by NO times PO equals Ni squared, where Ni is the intrinsic semiconductor material concentration. What is NO? NO is the thermal equilibrium concentration of free electrons, and PO is the thermal equilibrium concentration of holes in a material. And again, Ni is the intrinsic carrier concentration. At room temperature, guys, 300 Kelvin, each donor atom donates a free electron to the semiconductor material. This is what we agreed in the previous slide. So, in this case, the whole concentration can be calculated as follows. So in case of n-type material, the NO is going to be the same as N donor, and we can calculate the PO, the whole concentration, as Ni squared divided Nd. Okay, so this is for the n-type material. So the concentration of the holes will be the intrinsic concentration squared divided N donor. And the similar in case of the p-type material, in case of accepting electrons. So we can say the whole concentration is the same as N acceptor, and we can say in this case the N or electron concentration equals Ni squared divided Na. Next class, we will repeat this slide again and start solving some or solving example on the concentration and compare the intrinsic and concentrinsic and extrinsic concentration of the semiconductor material. What type we do prefer? What's the preferred n-type or p-type material, and the current flow in a semiconductor material. Thank you so much, guys. The class, as we mentioned, expect the recording on every Tuesday and Friday. We will have, as we mentioned, 2 recording classes per week. Please see the video. If you have any question, send me an email. I will reply to your email as soon as I can. We don't have homeworks yet. We just started. I believe maybe after the coming class, we may have the first homework. And please, guys, follow up any announcement on eCampus. Everything will be through eCampus. Every announcement or every homework will be available on eCampus. So please check eCampus regularly. Okay. Thank you so much and have a nice day. Bye.